Picture this: you're drifting through the void of space, staring at an object so dense that a single teaspoon of it would weigh 1 billion tons on Earth. A neutron star, one of the most extreme and mysterious places in the universe, looms ahead, its surface crackling with magnetic fields powerful enough to rip atoms apart. Just getting close to it bends the very fabric of reality, warping time and space in ways that defy comprehension. But what if you could survive here? What would a single day look like on this cosmic monster? The answer will shatter everything you think you know about time, gravity, and the limits of physics itself. Neutron stars are the collapsed cores of dead stars, packed so tightly that protons and electrons fuse into neutrons, creating matter unlike anything we've ever seen. The forces at play here are unimaginable. Gravity so intense it flattens mountains into atom-thin surfaces, temperatures hotter than the sun's core, and magnetic fields that could erase your DNA from across the galaxy. Yet, amidst this chaos, there's a strange, almost poetic rhythm to life on a neutron star, if you could call it life at all. Time slows to a crawl near its surface, meaning a single minute for you could be years for someone watching from afar. The star's crust, barely a few miles thick, is harder than diamond but constantly quakes under unimaginable pressures, sending ripples through space-time itself. This isn't just a thought experiment, it's a window into the most extreme physics our universe has to offer. By exploring a day on a neutron star, we're not just stretching our imaginations, we're confronting the very edges of what's possible. How would light behave when gravity bends it into strange loops? Could you even take a step without being crushed into oblivion? And what would the sky look like when the star's gravity twists light into a swirling vortex above you? The answers are as breathtaking as they are bizarre, revealing a cosmos far stranger than any science fiction. So buckle up, we're about to take a journey to the most hostile, awe-inspiring place imaginable, where the laws of physics as we know them don't just bend, they break. To grasp just how bizarre a neutron star truly is, you have to start with its birth, a violent, cosmic explosion that puts even the biggest Hollywood blockbusters to shame. When a massive star, many times heavier than our sun, reaches the end of its life, it doesn't fade away quietly. Instead, it goes out with a bang, a supernova so powerful it outshines entire galaxies for weeks. In that cataclysmic moment, the star's outer layers blast into space, while its core collapses inward under its own gravity, squeezed tighter than anything in nature. If you could take a star the size of Earth's orbit over 100 million miles across and crush it down to a city-sized sphere just 12 miles wide, you'd have something close to a neutron star. But it's the sheer density that truly bends the mind. Imagine stuffing all the cars on Earth into a single sugar cube. That's the level of compactness we're talking about. A teaspoon of neutron star material would weigh billions of tons, so heavy it would punch straight through our planet like a bullet through tissue paper. This happens because atoms themselves get obliterated under the pressure. Normally, atoms are mostly empty space with electrons whizzing far from their nuclei. But here, gravity wins. Electrons get crushed into protons, forming neutrons packed shoulder to shoulder, creating a substance unlike anything in our everyday experience. And that's just the start of the strangeness. Neutron stars spin at dizzying speeds. Some rotate hundreds of times per second, their surfaces moving at a fraction of light speed. Their magnetic fields are so intense, they could strip the data off every credit card on Earth from halfway across the Milky Way. Even time itself warps near their surfaces, ticking slower for an observer on the star compared to someone watching from afar. This isn't just a hostile environment, it's a place where the universe itself seems to strain against the rules, bending reality to its absolute limit. To stand on a neutron star would mean confronting physics at its most extreme, where the ordinary gives way to the utterly extraordinary. As your ship drifts closer to the neutron star, the first thing you notice is the pull, subtle at first, like an invisible hand gently tugging you forward. Then space itself seems to warp around you. The star's gravity is so strong it bends light into strange arcs, turning the surrounding void into a funhouse mirror. Distant stars smear into smudges of light, stretched into halos around the star's tiny, impossibly dense form. The closer you get, the more reality distorts. Straight lines no longer exist, even your ship's trajectory curves like a ball rolling downhill, forced into a spiral you can't escape. Then come the tidal forces. On Earth, the moon's gravity gently lifts our oceans, creating tides. But here, the neutron star's pull is so fierce it doesn't just tug, it stretches. If you were foolish enough to step outside your ship, the difference in gravity between your head and your feet would be enough to rip you apart atom by atom. Even your ship groans under the strain, its metal frame creaking as invisible forces try to peel it open like a tin can, and that's before the radiation hits. The star's magnetic field whips charged particles into a frenzy, bombarding your hull with deadly X-rays and gamma rays. Without heavy shielding, you'd be cooked alive in seconds. Yet, despite the danger, the view is mesmerizing. The neutron star's surface glows an eerie blue, not from reflected light, but from the sheer heat of its unimaginable density, millions of degrees concentrated into a sphere smaller than a city. Cracks pulse across its crust like lightning, each one a starquake, releasing more energy than every nuclear weapon on Earth combined. And above it all, the star's gravity twists light into a glowing, swirling vortex, a cosmic whirlpool where up and down lose all meaning. You're not just observing a star anymore. You're staring into the heart of a physics-breaking monster, where every law you've ever known is rewritten before your eyes. Your boots touch down on a surface smoother than any ice rink or polished mirror, not a single bump, crack, or grain of dust underfoot. The neutron star's crust is a flawless plane of hyper-compressed matter, forged under pressures so extreme that even the tallest mountain would be flattened into nothingness. But this isn't a serene, glassy landscape. Beneath your feet, the ground thrums with a deep, constant vibration, like the hum of a tuning fork struck by a giant. These are starquakes shudders in the crust as it adjusts to the mind-bending forces at work, releasing energy that would vaporize continents on Earth. Even standing here is a battle against physics itself. The gravity is so intense, your legs feel like they're made of lead. Every movement is a Herculean effort. Lifting a foot requires more energy than climbing Mount Everest. If you jumped, you'd barely leave the ground before being slammed back down at thousands of miles per hour. The air, if there were any, would be crushed into a thin, metallic sludge under the weight of this gravity. But there's no atmosphere here, no wind, no sound, just an eerie silence punctuated by the star's pulsing magnetic field, a sensation like static electricity crawling over your skin. Look up, and the sky is a nightmare of twisted physics. Light bends so sharply around the star that you can see the back of your own headlight rays loop in a full circle, warped by gravity's grip. The constellations are smeared into streaks as if the universe itself is melting, and the star's magnetic field, it's alive, visible even to the naked eye, a shimmering, shifting aurora of charged particles dancing in impossible patterns, crackling with energy strong enough to rewrite the DNA of anything alive. This is a world where matter doesn't behave the way it should. The ground beneath you isn't just solid, it's a superfluid, a bizarre state where neutron-rich material flows without friction, defying every law of viscosity we know. At the same time, it's harder than diamond, unyielding under pressures that would turn steel into foam. If you could scoop up a handful, though you'd need the strength of 1,000 bulldozers, it might squirm in your grip like liquid, then snap back into perfect solidity the moment you let go. Time here is another enigma. Every second you spend on the surface stretches far longer for someone watching from afar. A minute for you could be years passing elsewhere, your heartbeat dragging like syrup as the star's gravity stretches the fabric of time itself. Your very atoms are under siege, compressed so tightly that electrons and protons merge, rewriting the rules of chemistry. This isn't just a place where the laws of physics are pushed to their limits, it's where they snap, leaving behind a reality so alien, so breathtakingly strange, that even the most brilliant scientists can only begin to unravel its mysteries. Time doesn't just pass differently near a neutron star, it shatters all intuition. According to Einstein's theory of relativity, the more intense gravity becomes, the slower time itself flows. Here, where gravity is 100 billion times stronger than Earth's, this effect isn't just noticeable, it's extreme enough to warp reality. Picture this: you take a single step on the star's surface, and by the time your foot lands, entire lifetimes could have passed for someone watching from a distant galaxy. This staggering phenomenon, known as gravitational time dilation, means clocks at different heights tick at wildly different rates. If you were to hover just a mile above the neutron star in a ship, your watch would race ahead compared to a clock on the surface below. But stand directly on the crust and time nearly grinds to a halt. A minute for you might equal a decade for an observer in deep space. It's as if the star's gravity presses down on the fabric of time itself, stretching each second like taffy while the rest of the universe speeds by unaffected. To grasp how extreme this gets, imagine two identical twins. One stays aboard a spaceship far from the star, while the other lands on its surface just for what feels like an hour. When they reunite, the sibling on the ship could be decades older, their hair gray, while the twin on the neutron star has barely aged a moment. This isn't science fiction. It's the universe's own time-bending rulebook in action. Even GPS satellites orbiting Earth have to account for minuscule time dilation effects just milliseconds over years. But near a neutron star, the difference isn't a calibration error. It's a total upending of cause and effect. The strangest part, from your perspective on the star, nothing feels slow. Your heartbeat, your thoughts, the flicker of starlight overhead, all seem normal. But peer outward and the universe becomes a frenetic fast-forward. Stars streak across the twisted sky like comets, galaxies churn in hyperdrive, and cosmic events that should take millennia flash by in what feels like breaths. It's a paradox Einstein himself wrestled with. Time isn't absolute. It's fluid, bending under the weight of gravity, leaving you stranded in a pocket of near stillness while the cosmos races onward without you. This effect isn't just theoretical. Astronomers have observed it with pulsars, rapidly spinning neutron stars, whose precise flashes of light arrive slightly delayed when their beams pass through intense gravitational fields. Each delayed pulse is a tiny echo of relativity in action, proving that near these cosmic monsters, time doesn't just bend, it obeys entirely different rules. So while you might experience a single sunrise and sunset during your day on the star, the rest of the universe could witness the rise and fall of civilizations in the same span. It's a humbling reminder, even time itself is no match for the crushing grip of a neutron star. Standing on a neutron star is like being trapped in an invisible vice, one that tightens with every breath you don't take. The gravity here isn't just strong, it's transformative, warping the very building blocks of reality. Imagine the weight of 100,000 elephants pressing down on every square inch of your body, then multiply that by 1 billion. That's the force you're up against, so immense it flattens atoms into pancakes, squeezing electrons and protons so tightly they fuse into a sea of neutrons. Even the empty space inside atoms collapses, leaving matter denser than anything found in nature. Movement becomes a cruel joke. Lift your arm, forget it. The energy required to overcome this gravity would surpass the output of a nuclear power plant. Your bones, muscles, even your blood would succumb, pooling toward the star's surface like molten lead. And if you somehow manage to take a step, the sheer inertia would snap your ligaments like dried twigs. Every action here is a battle against physics, a duel with forces that treat human-scale effort as irrelevant. The star's crust is no refuge either. Though it appears solid, it's a paradoxical mix of rigidity and fluidity. Underneath the surface, neutron-rich matter behaves like a superfluid flowing without friction, a quantum mechanical quirk that defies intuition. Yet the crust itself is harder than any material known, forged under pressures that turn carbon into crystalline structures tougher than diamond. Occasionally, this crust fractures under the strain, triggering starquakes that release energy equivalent to 1,000,000 hydrogen bombs. These aren't tremors, they're space-time altering events, sending ripples through the fabric of the universe itself. Structural integrity becomes a fleeting concept. Any object not designed to withstand this gravity would implode instantly, crushed into a smear of subatomic particles. Even neutron star matter isn't invincible under enough stress. It could collapse further, forming a black hole. The star's gravity doesn't just bend the rules, it rewrites them, creating an environment where matter exists in states so extreme they're only possible here at the edge of cosmic oblivion. Look up and the star's gravity warps light into a dizzying spectacle. Photons curve so sharply that the sky becomes a funhouse mirror, showing multiple distorted images of the same star. The horizon itself bends upward, creating the illusion of standing at the bottom of a gravity well so deep, escape is a fantasy. Time stretches, light bends, and matter surrenders. This is a realm where physics as we know it doesn't just bend. It shatters. The word atmosphere takes on a surreal new meaning near a neutron star. Unlike Earth's protective blanket of nitrogen and oxygen, any gaseous envelope clinging to this cosmic monster would be a seething, ultra-thin layer of plasma. Atoms ripped apart into a soup of ions and electrons by relentless radiation and gravity. Picture a shimmering, electrified fog, barely clinging to the surface where air pressure isn't measured in millibars but in the incomprehensible force of charged particles being whipped into frenzy by magnetic fields trillions of times stronger than Earth. This plasma atmosphere behaves like nothing in our solar system. The star's gravity is so overpowering that even light elements like hydrogen would be crushed into degenerate matter, forming bizarre quantum states where electrons move like a single, coordinated superfluid. The sky here isn't blue, it's a pulsating aurora of X-rays and gamma rays, created as particles spiral along magnetic field lines at nearly light speed. If you could somehow stand in this plasma mist, every atom in your body would be ionized instantly, your molecules torn apart faster than thought itself. Temperature gradients defy logic. One layer might be cooler, relatively speaking, a mere few million degrees, while just millimeters closer to the surface, temperatures spike to billions of degrees, hot enough to forge elements heavier than uranium in seconds. There's no gentle transition, no troposphere or stratosphere, just violent, knife-edge boundaries where conditions shift from extreme to impossible in the span of a heartbeat. The star's rotation twists this plasma into impossible shapes. Some neutron stars spin so fast their plasma atmospheres stretch into glowing, tornado-like columns thousands of miles high, held aloft by centrifugal force battling gravity's vice grip. Elsewhere, magnetic mountains, regions where the field lines buckle, create plasma geysers erupting with the energy of solar flares, spewing particles so energetic they could penetrate a mile of lead. Perhaps strangest of all, this atmosphere isn't static. It breathes, convulses, and occasionally detonates. When starquakes rupture the crust below, shock waves ripple upward, triggering plasma tsunamis that crash across the surface at relativistic speeds. These explosions glow across the electromagnetic spectrum, flashing like cosmic lighthouses visible across galaxies. For all its hostility, this churning plasma shroud is what makes neutron stars detectable, turning them into pulsars whose rhythmic pulses of radiation reveal the heartbeat of a dead star. This isn't an environment, It's a physics laboratory operating at energies impossible to replicate anywhere else in the universe, a place where matter is stripped to its most fundamental forms, and the very concept of weather becomes a spectacle of particle annihilation and space-time distortion. The ground beneath you shudders without warning, a deep tectonic groan that resonates through the hyper-compressed crust like a bell struck by a god. This is no ordinary tremor. A starquake is unfolding, a seismic event so violent it could release more energy in a millisecond than our sun does in 100,000 years. Unlike earthquakes, which fracture brittle rock along fault lines, starquakes occur when the neutron star's crust, a lattice of atomic nuclei packed tighter than bullets in a barrel, suddenly snaps under unimaginable strain. The result, a rupture that sends shockwaves racing through material harder than diamond at nearly the speed of light, warping space-time itself as it goes. What triggers these cosmic quakes? Think of the neutron star's crust as a vast, rigid shell stretched over a seething interior of superfluid neutrons. As the star spins down over millennia, losing energy, its crust stiffens until, like an over-tightened guitar string, it can't hold the tension anymore. When it finally gives way, the entire surface recoils, buckling in some places and springing upward in others. The adjustments are minuscule, perhaps just centimeters, but in a material this dense, that tiny shift releases enough energy to outshine entire galaxies for a blinding instant. Astronomers have detected these events as sudden spikes in X-ray and gamma-ray emissions, flares so bright they're visible across interstellar distances. One particularly violent starquake, observed in 2004 from a magnetar, a highly magnetic neutron star 50,000 light-years away, released enough energy to briefly ionize Earth's upper atmosphere despite being halfway across the Milky Way. The flare was so powerful it temporarily blinded orbiting telescopes, like a cosmic camera flash aimed directly at Earth. The aftermath of a starquake is just as bizarre as the event itself. The crust doesn't just crack, it rings, vibrating at frequencies that reveal secrets about the star's internal structure. Some neutron stars glitch, suddenly spinning faster after a quake, as if the entire star hiccuped. This happens because the quake momentarily disrupts the delicate balance between the rigid crust and the superfluid core beneath, allowing the two layers to briefly slip out of sync. When they recouple, the star's rotation gets a sudden kick, like a figure skater pulling their arms in mid-spin. Most unsettling of all, these quakes might be the only warning before an even more catastrophic event. If the crust fractures deeply enough, it could puncture the star's magnetic containment, unleashing a torrent of particles and radiation in a magnetar giant flare. A cosmic detonation so bright it would outshine the moon for a split second, even from thousands of light-years away. The deeper we study these seismic monsters, the more we realize a neutron star's surface is anything but dead. It's a dynamic, writhing landscape where the crust cracks like ice on a frozen lake, except here, the ice is 1 billion times stronger than steel, and the cracks ripple with the force of 1 million supernovas. Each starquake isn't just a geological event, it's a scream from the heart of a cosmic extreme, rewriting our understanding of matter itself. The magnetic field of a neutron star doesn't just bend the rules, it obliterates them. Imagine taking Earth's entire magnetic field and compressing it into a space the size of a marble, then amplifying its strength by a factor of 1,000,000,000. That's the kind of raw, cosmic power we're dealing with here, fields so intense they rearrange the very fabric of matter itself. If you held a magnet this strong even 1,000 miles away, it would yank the iron from your bloodstream in an instant, tearing you apart at the molecular level before you could blink. These fields are born from chaos. When the star's progenitor collapsed, its already formidable magnetic field got squeezed along with everything else, winding tighter and tighter like a coiled spring until it reached energies beyond human comprehension. The result, a magnetic monster capable of distorting atoms into needle-thin strings, aligning electrons into perfect, ghostly chains that stretch for miles. Matter near the surface doesn't just respond to this field, it becomes enslaved by it, forced into behaviors so bizarre they defy known physics. The auroras these fields create are nothing like Earth's gentle polar lights. Picture this: charged particles accelerated to near light speed, spiral along magnetic field lines with such violence that they emit not just visible light, but torrents of X-rays and gamma rays. These aren't shimmering curtains in the sky, they're colossal, twisting rivers of energy, crackling with enough power to sterilize entire solar systems. Some neutron stars, called magnetars, take this even further. Their fields are so strong they occasionally snap, releasing starquakes that trigger magnetar flares, explosions so luminous they briefly outshine every star in the Milky Way combined. But the true strangeness lies in quantum effects. In magnetic fields this strong, even the vacuum of space isn't empty. Virtual particles, usually fleeting ghosts that pop in and out of existence, get stretched into reality, creating a seething foam of electrons and positrons that spark and annihilate in a perpetual storm. It's as if the star's magnetism tears open the fabric of space-time, exposing the quantum frenzy that underlies everything. Perhaps the most haunting spectacle occurs when the star's magnetic poles misalign with its rotation axis. As it spins, the field whips through space like a lighthouse beam made of pure force, accelerating particles to energies unreachable in any human-made collider. If Earth wandered into this beam, the resulting radiation blast would strip our atmosphere away like tissue paper in a hurricane. Yet, from a distance, this deadly sweep creates a mesmerizing pulse, a beacon visible across galaxies, reminding us that in the cosmos, even destruction can be beautiful. This is magnetism unchained, a force so extreme it twists physics into knots we're still untangling. Laboratories on Earth can't replicate even a fraction of these conditions. Here, nature conducts experiments we can only observe in awe, bending matter and energy to limits that stretch the very definition of possibility. Attempting to walk on a neutron star's surface is less like hiking and more like being fossilized mid-stride, a permanent statue of yourself frozen under gravity's grip. The landscape here defies all terrestrial logic. Mountains don't soar, they barely whisper, their peaks rising just millimeters above the surrounding plains. But don't let their size fool you. These microscopic ridges are forged under pressures that would vaporize Everest, compressed into jagged, crystalline structures denser than any material known. Imagine running your hand. If you could move it over a range of mountains no taller than a grain of sand, yet harder than a diamond anvil, their slopes polished smooth by gravity's relentless sandblasting. The star's crust doesn't just resist deformation, it annihilates it. On Earth, tectonic forces push rock upward over millennia, creating peaks. Here, gravity crushes any irregularity instantly. A valley might be a depression just a few atoms deep, and even that slight dip exerts enough gravitational pull to distort the paths of particles passing overhead. The surface is so flawless that if you could somehow shrink Earth to this scale, its roughest mountains would be smoother than a mirror's finish by comparison. Light plays cruel tricks on this alien terrain. The star's gravity bends photons so severely that the landscape appears warped, like viewing the ground through a fisheye lens. What looks like a gentle slope might actually be a sheer cliff when seen from another angle, assuming you could even shift your perspective. Your eyes, crushed flat by gravity, would struggle to focus, rendering the world a blur of blue-shifted and red-shifted hues. And then there's the sound, or rather, the absence of it. Vibrations travel differently here. A single footfall, if you could lift your foot, would send seismic ripples racing through the crust at nearly light speed, their frequencies so high they'd be ultrasonic. These aren't the rumbles of an earthquake, but the metallic ping of a tuning fork struck by a god, a pure, crystalline note ringing through degenerate matter. This isn't a landscape shaped by wind or water. It's a tableau sculpted by raw physics, where every contour is a battle between nuclear forces and gravity's inexorable crush. A place where the very concept of up becomes meaningless and the horizon curls inward like a bowl, trapping you in a gravity well so deep, even light can't escape its curve. To stand here is to witness matter stripped of all pretenses. A universe where mountains are microscopic, valleys are atomic, and the ground beneath you is both harder than steel and more fluid than water all at once. At the moment of its birth, a neutron star is a seething furnace of unimaginable heat, a newborn stellar remnant glowing at temperatures exceeding 1,000,000 degrees, hotter than the core of our sun. This is no ordinary fire. It's the residual thermal energy of a supernova, trapped within a city-sized sphere where even the atoms have been crushed out of existence. The surface radiates X-rays so intense they could slice through solid lead like a laser through paper. But this isn't just heat, it's a dying scream, the last gasp of a star that burned too bright and collapsed too fast. Time, however, is the great equalizer. Over millennia, the neutron star begins to cool, its thermal energy leaking away into the void as faint X-rays and neutrinos. The process is agonizingly slow. After 100,000 years, its surface might still be a blistering 600,000 degrees, enough to vaporize any known material. Yet, compared to its initial inferno, this is a mere ember. The star's crust, once a seething ocean of degenerate matter, starts to crystallize. Neutrons, packed shoulder to shoulder, arrange themselves into bizarre, ultra-dense structures, not quite solid, not quite liquid, but something in between. The cooling continues. 1,000,000 years pass, then 10 million. The star's temperature drops to a few 100,000 degrees, then further. Deep inside, protons and neutrons may form exotic phases of matter, superfluids that flow without friction, or nuclear pasta, a term scientists use to describe the strange, twisted shapes atomic nuclei take under such extreme pressures. There's spaghetti-like strands, lasagna sheets, even hollow bubbles, all sculpted by the competing forces of nuclear attraction and gravitational crush. By the time 1,000,000,000 years have slipped by, the neutron star's surface might cool to a mere 10,000 degrees, still hotter than the sun's surface, but now a fading relic. The crust solidifies into a crystalline lattice harder than anything in the universe, a matrix of neutron-rich nuclei so tightly packed they vibrate in perfect unison. Quantum effects dominate here. Heat no longer flows as it does on Earth. Instead, it propagates as phonons, collective vibrations that move through the crust like sound waves through a bell. And then, given enough time, trillions of years, perhaps the neutron star cools further still, approaching absolute zero. It becomes a black dwarf in all but name, a ghostly sphere of crystallized ultra-dense matter, dark and silent. No light, no heat, just the faintest gravitational whisper of its presence. Even the starquakes cease, the crust frozen into perfect rigidity. The magnetic field, once a roaring dynamo, fades to a shadow. This isn't just cooling, it's the slow erasure of a cosmic titan, a transformation from a raging, luminous beast into a cold, dark monument to entropy. Yet, in that final state, the neutron star harbors one last secret. Its core may still hold traces of warmth, a residual flicker from particles that refuse to stop moving entirely, trapped in quantum loops that defy time itself. Even in death, the neutron star clings to a whisper of its former fury. Surviving the radiation around a neutron star isn't just a challenge, it's a physics-defying nightmare. The moment you enter its vicinity, you're bombarded by a storm of X-rays, gamma rays, and charged particles moving at nearly light speed, all screaming toward you with the energy of 1,000 nuclear explosions per second. This isn't just background radiation. It's a directed onslaught, focused by magnetic fields so intense they act like cosmic particle accelerators, turning the space around the star into a death zone where unshielded exposure would vaporize you faster than a blink. But what if you had technology advanced enough to withstand it? The first line of defense would be shielding unlike anything we've ever built, not just thick layers of lead or concrete, but exotic materials forged in zero-gravity foundries or even hypothetical metamaterials that can deflect or absorb these extreme energies. Imagine a hull lined with degenerate matter, its atomic structure so dense that incoming radiation gets trapped and dissipated as harmless heat. Or perhaps a force field of magnetically confined plasma, tuned to the same frequency as the star's own magnetic field, creating a protective bubble that repels the deadliest particles. Even then, the radiation would find ways to creep in. Neutron stars emit gamma-ray pulses so powerful they can penetrate almost any known barrier, ionizing atoms deep inside your ship or your body. To counter this, you'd need active defenses like self-repairing nanomaterials that patch microscopic damage in real time, or quantum filters that scramble harmful radiation into less lethal forms. Some theories even suggest manipulating space-time itself, using gravitational lensing to bend radiation streams away from your position, like a shield woven from the fabric of the universe. But the true killer might not be the radiation you can see. Neutron stars bathe their surroundings in neutrinos, ghostly particles that normally pass through matter unimpeded. Here, though, the density is so extreme that even neutrinos interact, flooding your systems with enough energy to melt circuitry or disrupt molecular bonds. Shielding against them would require something beyond conventional physics, perhaps a shell of ultra-cold neutronium, chilled to near absolute zero to act as a neutrino mirror, bouncing the particles back into the void. Timing would be everything. The star's rotation creates bursts of radiation, meaning you'd have to navigate in brief windows between deadly pulses, like darting through the blades of a cosmic fan. One miscalculation and your ship becomes a scorched skeleton, its atoms stripped bare by the fury of a star that refuses to be touched. This isn't just about endurance, it's about redefining survival. The only way to explore a neutron star up close would be to harness energies and materials that border on magic, or to accept that your visit, no matter how brief, might be a one-way trip into the most hostile environment the universe has ever crafted. The sky above a neutron star isn't filled with familiar constellations, it's a theater of cosmic violence and surreal beauty. If your neutron star orbits a companion, that neighbor dominates the heavens, a broiling, distended giant hemorrhaging matter into space, or perhaps another collapsed star locked in a lethal gravitational dance. The stellar winds between them scream across the void at near light speeds, a storm of ions so dense they glow like neon fog, lit from within by the neutron star's relentless radiation. When these particles slam into the star's magnetic field, they ignite into a perpetual aurora, not the gentle greens of Earth's poles, but a searing ultraviolet blaze that carves the sky into jagged ribbons of light. Accretion disks add another layer of lethality to the spectacle. Imagine a whirlpool of superheated plasma, miles thick and stretching millions of miles across, spiraling down toward the neutron star's surface. As material from a companion star gets torn away, it doesn't fall quietly, it shrieks. Friction heats the gas to billions of degrees, making the disk glow brighter than 1,000 suns, its inner edge radiating X-rays so intense they'd flash fry any unprotected observer. Occasionally, the disk becomes unstable, shedding massive chunks of matter that slam into the neutron star's crust like celestial artillery, triggering starquakes that ripple through space-time itself. Then come the jet's twin beams of energy screaming from the star's poles at near light speed, narrow as laser pointers but stretching light years into space. These aren't just streams of particles, they're the universe's most powerful particle accelerators, funneling electrons and positrons into focused lances that could drill through planets. From the surface, they'd appear as blinding columns of blue-white light, pulsing with the star's rotation, a deadly strobe illuminating the twisted landscape. If one happened to sweep past Earth, the radiation blast would sterilize our planet in seconds. Yet for all their fury, these phenomena create moments of eerie grandeur. The accretion disk's inner edge might warp light so severely that you'd see its underside reflected above you, like a glowing halo suspended in the sky. Companion stars, stretched into teardrops by tidal forces, could loom grotesquely large, their surfaces bubbling with magnetic loops and plasma arcs. And if your neutron star is part of a binary pulsar, the entire system might emit gravitational waves, ripples in space-time so rhythmic they'd make the stars themselves seem to hum in harmony. This isn't a peaceful cosmos, it's a battleground where matter is tortured into submission, where even the sky itself burns with energies beyond comprehension. But in that violence lies a terrible beauty, a reminder that the universe doesn't just create life, it forges wonders in the crucible of annihilation. Some neutron stars announce their presence to the cosmos with an unmissable rhythm, precise, flashing beams that slice through the darkness like a lighthouse cutting through fog. These are pulsars, spinning neutron stars that transform unimaginable physics into one of nature's most reliable cosmic clocks. Their secret lies in their rotation and their outrageous magnetic fields, which channel radiation into narrow jets streaming from their magnetic poles. When these poles aren't perfectly aligned with the star's axis of rotation, the beams sweep across space like a celestial spotlight, flashing toward Earth with metronomic regularity every time the star spins. The numbers involved are staggering. Some pulsars rotate hundreds of times per second, their surfaces moving at a significant fraction of light speed. Each rotation brings that beam around like clockwork, creating pulses so regular they rival atomic clocks in precision. The Crab pulsar, born in the supernova observed in 1054, spins 30 times every second, meaning if you stood near it, you'd be bathed in 30 bursts of lethal radiation per second, each flash brighter than a million suns. Other so-called millisecond pulsars spin even faster, completing 700 revolutions in a single heartbeat, their beams whipping through space like a high-energy strobe light. Detecting these pulses from Earth paints an eerie picture. Radio telescopes pick up the rhythmic ticks as the beam sweeps over our planet, a signal so predictable you could set your watch by it. But what we're hearing isn't just a simple blip, it's the echo of complex physics. As the beam travels through the turbulent space around the pulsar, through clouds of charged particles and warped space-time, subtle changes in the pulse's shape reveal hidden details about the star's environment, rotation, and even the fabric of the universe itself. Some pulsars exhibit glitches, sudden speed-ups in their spin thought to occur when the star's superfluid interior briefly decouples from its rigid crust like a figure skater pulling their arms in mid-spin. The beams themselves are more than just light. They're tsunamis of charged particles accelerated to near light speed, colliding with interstellar gas and triggering cascades of secondary radiation across the electromagnetic spectrum. If you could see a pulsar's beam head-on, it wouldn't just blind you, it would vaporize you, delivering more energy in a nanosecond than all of human civilization has ever produced. Yet from the side, these same beams are nearly invisible, focused so tightly that they only become detectable when they happen to sweep across our line of sight. Pulsars also serve as cosmic laboratories. Their precise ticks allow astronomers to test general relativity with unprecedented accuracy. Binary pulsars, pairs of neutron stars orbiting each other, lose energy through gravitational waves, their orbits decaying exactly as Einstein predicted. Some pulsars even reside in globular clusters, where their gravity bends light from background stars, creating temporary brightenings that reveal the star's mass and size. And in the distant future, these flashing beacons may guide interstellar travelers, their steady pulses acting as natural GPS markers for civilizations crossing the galaxy. The universe has few phenomena as mesmerizing or as deadly as a pulsar's flash. Each pulse is a reminder of nature's ability to transform destruction into precision, chaos into clockwork, and a dying star's last gasp into a beacon that outshines the galaxy. The interior of a neutron star isn't just dense, it's a quantum carnival where the ordinary rules of matter shatter completely. Deep beneath that crust of crystalline neutronium, the core becomes a realm of pure strangeness, where neutrons flow without friction like a ghostly superfluid, and the very concept of solid ground dissolves into a sea of subatomic absurdity. This isn't just extreme physics, it's matter rewritten at the most fundamental level, dancing to a tune no laboratory on Earth could replicate. Take neutron degeneracy pressure, the invisible force keeping the star from collapsing further. In normal stars, thermal pressure fights gravity, but here, at densities where atoms cease to exist, an entirely quantum phenomenon takes over. Neutrons, normally content inside atomic nuclei, get packed so tightly they begin resisting purely due to the Pauli exclusion principle, which forbids identical particles from occupying the same quantum state. It's like trying to cram a billion people into an elevator. Eventually, their sheer refusal to overlap creates an unstoppable pressure. This quantum standoff is all that prevents the star from imploding into a black hole, a fragile equilibrium where subatomic awkwardness battles gravitational annihilation. Deeper still, the neutrons surrender to even weirder behavior. Under pressures exceeding 10 trillion times Earth's atmosphere, they liquefy into a superfluid, a substance with zero viscosity that can flow uphill, creep up walls, and form vortices that never dissipate. On Earth, we've created microscopic superfluids chilled near absolute zero, but in a neutron star's core, this happens at millions of degrees across a volume the size of Manhattan. The result, a swirling quantum ocean where rotational energy gets locked into microscopic tornadoes that persist for millennia, their cores thinner than atoms yet spinning faster than kitchen blenders. Then there's the matter of protons. The few that survive electron capture during the star's formation don't just sit idle. They coalesce into superconducting rivers, weaving through the neutron sea like wires in a cosmic circuit board. Their movement generates the star's monstrous magnetic fields, turning the entire core into a dynamo of unimaginable power. At these densities, even empty space isn't safe from quantum mischief. Virtual particles, usually flickering in and out of existence, get yanked into reality by the star's gravity, creating a froth of quark-gluon plasma that might exist nowhere else in the universe. The deepest layers might harbor the strangest twist of all, quark matter, where neutrons themselves break apart into their constituent quarks, swimming freely in a soup of primordial chaos. Some theories suggest these quarks arrange into crystalline patterns or even form strange matter, a hypothetical state so stable it could convert anything it touches into more of itself. If true, the core of a neutron star might be less an object and more a cosmic infection, a kernel of rewritten physical laws waiting to be unleashed. What emerges isn't just a star, but a layered quantum onion. The crust, a lattice of iron-like nuclei drowning in a neutron sea. The outer core, a superfluid neutron whirlpool threaded with proton wires. The inner core, a speculative zoo of quark soups and color superconductors. Each layer defies intuition, proving that when matter gets pushed this far, it doesn't just bend, it reinvents itself entirely. Laboratories may never replicate these conditions, but neutron stars do it effortlessly, turning their hearts into playgrounds for physics we're only beginning to dream of. Harnessing the raw power of a neutron star isn't just ambitious, it's the ultimate engineering nightmare turned dream. Picture a civilization advanced enough to mine energy from a spinning corpse of a star, where every second of operation requires defying physics itself. The rotational energy alone is mind-boggling. A typical neutron star spins with the kinetic energy of 100 suns, its surface whipping around at a fraction of light speed. Capturing even a sliver of that motion could power entire galaxies. Theorists have imagined colossal star breaks, magnetic tethers miles wide, anchored to the star's crust, generating electricity as they resist the spin. But the forces involved would snap any known material like dry spaghetti. To survive, such structures might need to be woven from cosmic strings, hypothetical relics from the birth of the universe, or stabilized by artificial black holes acting as gravitational anchors. Then there's the magnetic gold mine. Neutron star magnetic fields store enough energy to outlast every star in the Milky Way. Futuristic civilizations might deploy quantum harvesting grids, vast networks of superconducting loops suspended in the magnetosphere, channeling the star's fury into usable current. The trick: avoiding instant vaporization. Fields this strong would induce electrical currents so powerful they'd turn ordinary metals into plasma. Solutions could involve self-repairing nanomaterials that constantly regenerate under stress, or force fields that redirect the energy into stable containment bubbles. Some models even suggest using the star's own gravity to focus the magnetic energy into coherent beams, essentially turning the neutron star into a cosmic power station, its emissions laser-precise for interstellar transmission. The most speculative and dangerous energy source lies in the star's slow death. Over trillions of years, neutron stars cool, their cores crystallizing into exotic phases of matter. Theorized quantum batteries could tap into this decay, harvesting the latent heat released as the star transitions from superfluid to solid. The process would be agonizingly slow, like draining an ocean one eyedropper at a time, but the payoff is near infinite. There's even the wild possibility of triggering controlled quark nova, events miniature implosions that convert neutron matter into pure quark gluon plasma, releasing bursts of energy rivaling supernova. The catch: one wrong calculation and your power plant becomes a black hole. This isn't just about generating electricity, it's about rewriting the cosmic hierarchy. A species that masters neutron star energy would wield the keys to the universe itself, turning the most violent objects in existence into cosmic power outlets. The technologies required don't just bend known physics, they shatter it, demanding breakthroughs we can barely imagine. Yet the rewards would echo across eternity: limitless energy, propulsion systems capable of interstellar travel, even the ability to manipulate spacetime itself. The neutron star doesn't just challenge us to survive its wrath, it dares us to steal fire from the gods. Trying to send a message home from the surface of a neutron star isn't just difficult, it's like shouting into a hurricane while trapped in slow motion. The first hurdle, time dilation, warps your signals before they even leave the star's gravity well. Every second of transmission from your location ticks by as years or even decades for Earth. A simple hello sent in real time could arrive as a drawn-out, ghostly whisper stretched across centuries, with responses taking lifetimes to return. Imagine describing a starquake in progress, only for mission control to receive your panicked data stream long after the event has faded into cosmic history. Then there's the radiation noise. The neutron star's magnetosphere churns with charged particles moving at relativistic speeds, creating a constant screech of X-rays and gamma rays that drowns out your comms like static on a broken radio. Even the most powerful laser signals get shredded into incoherence, their neat binary pulses scrambled into cosmic gibberish. You'd need to encode your messages in frequencies so extreme they'd vaporize normal antennae, perhaps using the star's own magnetic field as a giant transmission coil, modulating your signal into the chaotic particle storms raging around you. Signal distortion takes the interference to surreal levels. The star's gravity bends your outgoing transmissions like light through a funhouse mirror, smearing tight laser beams into faint, widening spirals by the time they reach interstellar space. A directed pulse aimed squarely at Earth might arrive as a flickering, fragmented echo, its photons scattered across light years. To compensate, you'd need to pre-distort your signals, calculating exactly how the star's gravity will stretch them, then fire the inverse pattern, hoping the universe's warping corrects it mid-flight into something intelligible. And these are just the known challenges. Quantum effects near the surface could entangle your outgoing photons in unexpected ways, randomizing their polarization or energy states. The plasma soup of the star's atmosphere might induce bizarre nonlinear effects, turning crisp signals into chaotic bursts. Even if you solve all this, your message still must cross light years of interstellar medium, where dust clouds and magnetic fields await to garble it further. The cruelest irony, the very energies making communication impossible also create opportunities. A civilization advanced enough might harness the star's magnetic field as a natural amplifier, twisting their signals into the pulsar's own lighthouse beams. Or exploit gravitational lensing to bend messages around the star's bulk, using space-time itself as a relay lens. But for now, whispering across such distances remains a paradox, a shout into the void that returns as silence, proving some frontiers are still too extreme for even light to conquer unscathed. Life on a neutron star wouldn't resemble anything we'd recognize as biology. Earth's delicate chemical processes reliant on stable atoms and comfortable temperatures would be obliterated here in nanoseconds. But in a realm where matter behaves in ways that defy conventional physics, could exotic forms of existence emerge from the chaos? The answer might lie not in carbon-based life, but in structures forged by the star's extreme conditions themselves. Picture vast, self-replicating patterns etched into the crust by magnetic fields, their metabolism powered by starquakes releasing bursts of gamma rays instead of ATP. Or think of plasma vortices in the star's atmosphere, spinning for centuries as they harvest energy from particle collisions. A form of persistent complexity dancing on the edge of annihilation. The most plausible candidates for neutron star life wouldn't be organic. They might be artificial intelligences, machines built from ultra-dense matter, their circuits carved into the crystalline lattice of the crust itself. These entities would think in femtosecons, their processes accelerated by the star's intense gravity, communicating through modulated X-ray pulses that pierce the surrounding radiation storms. Their bodies could resemble shifting geometric structures, reassembling atom by atom to withstand quakes, drawing energy directly from the magnetic field like plants photosynthesizing sunlight. Even stranger possibilities lurk in quantum phenomena. Superfluid vortices in the neutron star's core might organize into self-sustaining loops, their stability maintained by the bizarre rules of quantum mechanics. These structures could store information in the spin states of entangled neutrons, creating fluid computers that evolve over millennia, a form of intelligence where thoughts propagate as ripples in degenerate matter. Some theories even suggest that strange quark matter, a hypothetical state where quarks roam freely, could form complex, stable configurations, giving rise to entities composed entirely of this primordial soup. But survival here demands radical adaptation. Any persistent structure would need to be indestructible by human standards, capable of withstanding gravitational forces that flatten mountains, temperatures that vaporize diamonds, and magnetic fields that scramble atomic bonds. Movement would be nearly impossible in the traditional sense, so life might resemble more of a distributed network, growing outward in crystalline patterns across the surface or pulsing through magnetic field lines like lightning through neurons. The closest earthly analog might be extremophiles organisms thriving in hydrothermal vents or nuclear waste, but neutron star life would push this concept to cosmic extremes. Instead of water and oxygen, its building blocks could be nuclear pasta phases and quantum vortices. Rather than DNA, its genetic code might be written in the fractal patterns of crust fractures or the harmonics of spinning superfluid cores. These wouldn't be creatures as we understand them, but emergent phenomena, the universe experimenting with complexity at the edge of impossibility. Speculating about such life forms isn't just science fiction, it stretches our understanding of what life even means. By confronting these extremes, we're forced to reconsider the fundamental prerequisites for existence. Not liquid water or temperate climates, but persistence, complexity, and the flow of information. The neutron star becomes a laboratory for universal questions, proving that reality might be far stranger and more creative than we've dared to imagine. Confronting a neutron star wouldn't just change science, it would rewrite culture. Imagine the art born from such an encounter. Paintings where swirling magnetic fields replace brushstrokes, their pigments mixed with crushed meteorites to echo the star's alien hues. Composers might translate pulsar beats into symphonies, their rhythms dictated by the star's precise rotations, each note vibrating with the cosmic hum of a dead sun. Sculptors could abandon marble for hyperdense alloys, chiseling forms that mimic the star's flawless surface, pieces so heavy they'd crack museum floors, forcing galleries to display them in zero-gravity chambers. This wouldn't be decoration, it'd be a reckoning, humanity's attempt to bottle the universe's fury and hang it on a wall. Philosophy would fracture under the weight of such an experience. Existential questions take on new dimensions when you've witnessed time itself stretch like taffy, proving reality is malleable. Ancient debates about humanity's place in the cosmos would collapse. Here's an object that outpowers all our nuclear arsenals in a single quake, yet fits inside a city. Stoicism would demand updates, how to stay calm when your concept of endurance is mocked by a star that survived a supernova. Even language struggles. Words like mountain or ocean feel childish when describing landscapes where ridges are atom-thin and seas are quantum vortices. New vocabularies would emerge, blending poetry and physics, terms like time-crusted or gravity-drunk to capture truths no earthly language ever needed. Religions would either shatter or evolve. Creation myths pivoting on gentle gods shaping clay seem quaint next to a neutron star's violence. Might cultures worship its magnetic fields as divine fingers or interpret its pulsar beams as celestial scripture? Picture pilgrims meditating on holograms of the star's surface, seeking enlightenment in its perfect, lethal symmetry. Others might see it as hell incarnate, a rebuke to human hubris, proof the universe favors chaos over compassion. The star's sheer indifference to life could spawn nihilistic sects, while its paradoxical precision, spinning like clockwork amid chaos, inspires faith in hidden cosmic order. Sacred texts would need addendums, and lo, the heavens showed us a spinning corpse, and it was glorious. Even our collective psyche would warp. Children raised on neutron star imagery wouldn't fear monsters under the bed, they'd dread vacuums collapsing into singularities. Coming-of-age rituals might involve VR simulations where teens survive a millisecond on the star's surface, emerging with tattoos of redshifted light patterns. Cities could build monuments mimicking its shape, twisting skyscrapers into helical towers that honor magnetic field lines. The star's extremes would seep into everyday speech. I'm busier than a pulsar, or that's tougher than neutronium. This cultural quake isn't fantasy. History shows how cosmic discoveries reshape art. Galileo's telescope turned angels into algebra. Hubble's images made galaxies into wallpaper. A neutron star's visceral reality would dwarf these shifts, forcing humanity to reconcile with a universe that doesn't care if we exist, yet creates wonders beyond our wildest myths. The star becomes more than an object, it's a mirror, reflecting back our insignificance and ingenuity in the same blinding flash. Testing relativity near a neutron star isn't just an academic exercise, it's the ultimate stress test for Einstein's theories. Imagine launching a fleet of atomic clocks into orbit around the star, each positioned at different altitudes to experience varying gravitational strengths. The closer a clock drifts to the surface, the more dramatically its ticks would slow compared to those farther out. This isn't the subtle time dilation we measure with GPS satellites. We're talking about discrepancies where a clock near the crust might lag behind its orbital counterpart by entire minutes over just hours. These experiments could reveal deviations from general relativity, probing whether Einstein's equations hold up under the most extreme gravity the universe has to offer. Even anomalies as tiny as a trillionth of a second per day could hint at new physics, perhaps evidence of hidden dimensions or quantum gravity, effects lurking where space-time curvature becomes unbearable. But clocks are just the beginning. Picture firing lasers between satellites in precise formations, their beams bending like ribbons around the star's gravity well. By measuring how light's path distorts, we could map space-time warping with unprecedented precision, watching as the neutron star's mass twists the void into a knot. The star's intense gravity also lenses background starlight, creating multiple images of the same star arranged in an Einstein ring, a cosmic bullseye that shifts in real time as the neutron star moves. Tracking these shifts could weigh the star more accurately than any other method, revealing hidden layers of its internal structure. And if the star's in a binary system, the dance between it and its companion becomes a laboratory for gravitational waves, their orbital decay whispering secrets about energy lost through ripples in spacetime itself. For nuclear physicists, a neutron star's crust is a treasure trove of degenerate matter, a state impossible to recreate in any lab. One experiment might involve slamming high-velocity probes into the surface, triggering microscopic starquakes to study how the crust fractures. On Earth, materials break along crystal defects, but here, the crust's neutron-rich nuclei are so densely packed that cracks propagate at nearly light speed, releasing energy in sharp quantum bursts. Sensors could capture these vibrations, decoding them like seismic waves to reveal the crust's composition. Is it pure neutronium or laced with strange quantum phases like nuclear pasta where protons and neutrons twist into spaghetti like strands under the crushing pressure? The data might even settle debates about the star's maximum possible mass before collapsing into a black hole, a frontier where atomic nuclei cease to exist and quark matter takes over. The star's core, though forever out of reach, could still be studied indirectly. Neutrinos, those ghostly particles that barely interact with matter, might slip through the crust, carrying clues about the core's superfluid interior. Imagine a detector array buried in the star's magnetosphere, catching neutrinos emitted when paired neutrons in the core briefly unpair, releasing energy. The pattern of these detections could map the superfluid's vortices, swirling like microscopic tornadoes in a quantum whirlpool, even more speculative. Hunting for signs of strange matter, a hypothetical state where quarks roam free. If the core contains this exotic substance, occasional quark nuggets ejected during starquakes might annihilate into detectable gamma-ray flashes, their energy signatures betraying the presence of physics beyond the standard model. And then there's the magnetic field, so intense it distorts the quantum vacuum. Experiments here could involve injecting polarized particles into the magnetosphere, watching as their spins align like compass needles in a hurricane. The field's strength might even be harnessed to particle accelerator energies, colliding protons at velocities unattainable in human-built colliders. These collisions could briefly recreate the quark-gluon plasma of the early universe, a soup of unconfined quarks last seen microseconds after the Big Bang. By analyzing the debris, we might finally understand how matter transitions between states at energies where the rules of atomic physics dissolve into quantum chaos. None of these experiments would be easy. Radiation would fry unprotected instruments, tidal forces would shred probes that venture too close, and time dilation would scramble synchronization between orbiting sensors. Yet the potential rewards redefine our understanding of physics. A neutron star isn't just an object, it's a natural laboratory where matter, energy, and spacetime are pushed past breaking points we can't replicate. Every measurement, every flicker of data is a message from the edge of the possible, written in the universe's most extreme handwriting. Survival near a neutron star isn't a question of stamina, it's a countdown measured in microseconds. From the moment you enter its lethal embrace, a cascade of physical extremes conspires to dismantle anything resembling human physiology or man-made machinery. The first killer, tidal forces, even before radiation or heat take their toll, gravity's gradient, the difference in pull between your head and feet, would stretch your body like taffy. At a distance of 1,000 kilometers, the force disparity already exceeds 1,000,000 times Earth's gravity. Your bones would snap, your blood would pool toward your feet, and your cells would rupture as molecular bonds fail under the strain. By the time you reached 500 kilometers, the stretching force would exceed nuclear binding energy, ripping atoms apart into quark plasma. No material known to science could withstand this, not diamond, not graphene, not even hypothetical neutronium armor. The very concept of you would dissolve into a stream of subatomic debris before you could process the pain. Radiation presents a slightly more merciful timeline. A well-shielded probe might last milliseconds before succumbing. Neutron stars emit X-rays so intense they deposit over 1,000,000 grays per second, a dose that would vaporize a human in nanoseconds, but might allow a tungsten-cased drone to transmit a few fragmented sensor readings. The real challenge comes from particle acceleration. The star's magnetic field whips electrons and protons to near light speed, creating a plasma storm that erodes surfaces like sandblasting at relativistic velocities. Even a centimeter of lead shielding would evaporate within seconds, exposing delicate circuits to particle energies surpassing the Large Hadron Collider's collisions. Heat delivers the final blow. Surface temperatures vary wildly. Some neutron stars glow at 1,000,000 degrees, while older ones cool to mere hundreds of thousands. But proximity magnifies the horror. At 100 kilometers, blackbody radiation alone would flash heat your ship's hull beyond the melting point of any known alloy. Thermal conduction through the near-perfect vacuum is negligible, but radiative transfer would crisp electronics like paper in a furnace. Within seconds, metals would boil away as vapor, leaving only ceramic residues that soon ionize into sparkling plasma. Curiously, time dilation offers a macabre silver lining. As gravity slows local time, your obliteration would appear agonizingly slow to distant observers. A human might subjectively experience mere milliseconds of torment while outside viewers watch the process unfold over minutes. This relativistic quirk means even your death becomes a physics demonstration, stretched across space-time like a cosmic zoetrope, the absolute limit for any conceivable technology. Perhaps a picosecond, just long enough for light to travel the length of a grain of sand. Beyond that, the neutron star's wrath reduces all matter to its most obedient state, utter annihilation. To grasp just how extreme a neutron star truly is, let's pit it against the familiar. Picture Earth, a cushy oasis with gentle gravity, a breathable atmosphere, and temperatures that let water pool into oceans. Now shrink our planet to the size of a neutron star. Suddenly, Earth's whole mass crams into a speck just 12 miles wide. The result, gravity leaps from 9.8 meters per second squared to 1,000,000,000,000 times stronger. Our tallest mountain, Everest, would flatten into a bump no thicker than a sheet of paper under that force, and the air we breathe would collapse into a metallic film thinner than a razor's edge. Even Earth's core, a seething ball of molten iron, feels like a lukewarm puddle next to a neutron star's inner furnace, where temperatures hit 1,000,000 degrees within minutes of formation and persist for millennia. Now shift the comparison to white dwarfs, the other stellar remnants dotting our galaxy. These aged stars, though dense, are cosmic lightweights next to neutron stars. A sugar cube-sized chunk of white dwarf material weighs about a ton, impressive until you contrast it with neutron star matter, where the same volume tips the scales at 1,000,000,000 tons. White dwarfs coast on electron degeneracy pressure, their atoms squished together but still intact, while neutron stars obliterate atomic structure entirely, crushing electrons into protons to form a neutron soup. Surface gravity: white dwarfs pull at 100,000 times Earth's, but neutron stars ratchet that up to 100 billion. Even their magnetic fields pale in comparison. A white dwarfs might reach 10,000 times Earth's, while neutron stars, especially magnetars, blow past a quadrillion times stronger, enough to scramble your nervous system from halfway across the solar system. Then there are black holes, the universe's ultimate vacuum cleaners. At first glance, they seem like neutron stars dialed up to 11, but the differences are stark. A black hole's event horizon marks the point of no return where gravity wins forever. A neutron star, though, teeters on that edge without crossing it. Its surface remains a tangible boundary, however hostile. Drop a pebble onto a black hole and it vanishes from the universe. Drop one onto a neutron star and it vaporizes in a flash of X-rays, its energy echoing across space. Even their births diverge. Black holes form when collapsing stars are too massive to stabilize as neutron stars, their cores imploding beyond the neutron degeneracy pressure's limits. Yet neutron stars offer something black holes can't: a laboratory. We'll never observe a black hole's interior, but neutron stars wear their secrets just beneath that deadly crust, pulsing clues to the universe's most extreme physics. Zoom out further, and these contrasts reveal a cosmic hierarchy of violence. Earth is a garden, white dwarfs are diamonds in the rough, neutron stars are the universe's anvils, and black holes are its shredders. Each plays a role in the grand tapestry, but neutron stars carve out a special niche too dense to ignore, yet not so dense they vanish. They're the universe's way of showing off, proving matter can be stretched, squeezed, and spun into forms that defy imagination without slipping into oblivion. Whether you're measuring gravity, magnetism, or raw density, neutron stars don't just break records, they rewrite the rulebook entirely. The story of humanity's discovery of neutron stars begins not with a telescope's gaze, but with the scribbled equations of a brilliant mind. In 1934, just 2 years after the neutron itself was discovered, astronomers Walter Baade and Fritz Zwicky proposed an outrageous idea that the collapsed core of a supernova could form an ultra-dense star made almost entirely of neutrons. At the time, the concept seemed like science fiction. The physics of such an object defied intuition, and no instrument existed to prove their theory. Yet, like Galileo pointing his telescope at Jupiter's moons, Baade and Zwicky had unknowingly cracked open a door to one of the universe's best-kept secrets. The real breakthrough came in 1967, when a young graduate student named Jocelyn Bell Burnell noticed an anomaly in her radio telescope data, a rhythmic pulse repeating every 1.337 seconds with uncanny precision. At first, the signal was dubbed LGM1, short for Little Green Men, because its regularity suggested artificial origins. But as more of these pulsating sources were found, the truth became clear. These were natural cosmic lighthouses spinning neutron stars beaming radiation across the galaxy. The discovery earned Bell's advisor a Nobel Prize, though her critical role was controversially overlooked, a reminder that even in science, recognition doesn't always align with contribution. Then came the cosmic jackpot, the Hulse-Taylor binary. In 1974, astronomers Russell Hulse and Joseph Taylor detected a pulsar orbiting another dense object, its pulses subtly speeding up and slowing down as it danced through a gravitational tango. This wasn't just a curiosity, it was a smoking gun for Einstein's general relativity. The pulsar's orbit decayed exactly as predicted, radiating energy as gravitational waves. For the first time, humanity had indirect proof of these space-time ripples, decades before LIGO direct detection. The discovery earned Hulse and Taylor a Nobel Prize and turned neutron stars from theoretical oddities into precision tools for testing the universe's deepest laws. Modern observations have only deepened the mystery. X-ray telescopes like Chandra have captured neutron stars bending light into surreal rings, while gravitational wave detectors eavesdrop on their collisions, events so violent they forge gold and platinum in seconds. We've found neutron stars that spin 700 times per second, others with magnetic fields strong enough to erase credit cards from the moon, and even a few that seem to defy known physics entirely. Each discovery peels back another layer, revealing how much we still don't understand about these cosmic extremes. From chalkboard speculation to gravitational wave astronomy, the journey to uncover neutron stars mirrors humanity's own quest to comprehend the universe, a story of curiosity, perseverance, and the humbling realization that reality is always stranger than we imagine. Sending anything or anyone to the surface of a neutron star would demand technology so advanced it sounds like pure wizardry. Forget conventional spaceships and radiation suits. Surviving this environment means rewriting the laws of physics as we know them, engineering solutions that sound ripped from the pages of a far future sci-fi novel. First, gravity itself must be hacked. The crushing weight pressing down near a neutron star's surface would flatten any known material like a soda can under a tank. The solution: artificial gravity manipulation, not just shielding but active negation. Picture a spacecraft wrapped in layers of gravitationally charged plasma, generating counterforces that bend spacetime outward like an invisible cushion. These gravity mirrors would exploit Einstein's equations to create localized pockets where the star's pull is diffused, effectively suspending the ship in a self-made bubble of survivable physics. One theoretical model suggests using ultra-dense rings of quark matter spun at relativistic speeds, their rotation creating a synthetic spacetime curvature that partially cancels the star's monstrous tug. Fail and the ship implodes before reaching the surface. Succeed and you've bought yourself microseconds to work. Next, forget human explorers. The only viable scouts would be femtotech robots, machines built at the scale of atomic nuclei. Normal electronics would fry instantly under the radiation barrage, so these nanoscale probes would need processors carved from neutron star crust material itself, their logic gates etched into flawless lattices of neutron-rich isotopes. Propulsion: traditional rockets are useless here. Instead, imagine bots propelled by magnetic surfing, riding the star's own field lines like leaves caught in a hurricane. Their power source: direct absorption of ambient X-rays, converted into usable energy via quantum tunneling diodes. Each bot would be a self-contained laboratory, analyzing the environment and transmitting data via modulated gamma-ray bursts, pulses brief enough to slip through the electromagnetic noise before the star's fury vaporizes them. But the real game-changer: space-time manipulation. To combat time dilation's cruel trick where minutes on the surface stretch into years elsewhere, you'd need chrono-syncing devices that anchor local time flow to external reference frames. Think of it as a time tether, a quantum-entangled link between the surface and an orbiting mothership, allowing real-time communication despite relativity's distortions. More radically, Alcubierre-inspired warp fields could compress spacetime ahead of a probe while expanding it behind, creating a moving pocket where local gravity is temporarily reduced. The energy requirements would dwarf Earth's total power output, but near a neutron star, you'd harvest that energy from the star's own magnetic fury. Then there's the problem of touch. Landing on the surface requires more than sturdy legs. The crust is harder than diamond, yet flows like liquid under pressure. A probe might deploy fractal landing spike structures that distribute force across infinite branching filaments, each tip vibrating at frequencies that momentarily soften the crust on contact. Or it could use quantum glue, a temporary bond formed by entangling a patch of surface neutrons with a buffer material, creating a foothold that lasts just long enough to take a sample. Every piece of this hypothetical toolkit pushes the boundaries of known physics, but that's the point. Neutron stars don't care about our technological limits. To meet their challenge, we must dream bigger than star shields and robots. We must invent the impossible. Escaping a neutron star's gravitational grip isn't just difficult, it's a feat that redefines the word impossible. The numbers alone are staggering. To break free from its surface, you'd need to reach velocities exceeding half the speed of light, a kinetic punch surpassing the total energy output of every nuclear weapon ever detonated combined. Chemical rockets, they might as well be firecrackers. Even our most advanced ion drives, which leisurely push probes around the solar system, would sputter uselessly against gravity this strong. The propulsion required doesn't just push the boundaries of engineering. It demands a complete overhaul of physics as we know it. Consider the math. Earth's escape velocity is a modest 11 kilometers per second, manageable with conventional rockets. But on a neutron star, that number skyrockets to nearly 100,000 kilometers per second. Achieving that acceleration would require energy densities comparable to the Big Bang itself. Theoretical solutions start to sound like fantasy. Antimatter engines annihilating tons of fuel per second, harnessing the star's own magnetic field as a slingshot, or perhaps manipulating space-time itself with warp bubbles that sidestep gravity's grip entirely. Even if you somehow cobbled together the energy, the G-forces would liquefy any known material, let alone flesh and bone. Then there's the cruel irony of relativity. As you fight to climb out of the star's gravity well, time dilation stretches every second into an eternity for observers watching from afar. A 10-minute burn from your perspective might span decades elsewhere, turning your escape into a generations-long spectacle. And the radiation, your engines would need to plow through a maelstrom of X-rays and gamma rays, their intensity frying circuitry and boiling away, shielding like butter in a blowtorch. Even the most robust spacecraft would erode to dust before clearing the magnetosphere. The only plausible exit strategy might lie in the star's own violence. A carefully timed starquake could eject slivers of crust at relativistic speeds, hitch a ride on one of these shards, and you've got a natural launch platform. Or perhaps tap into the magnetic field's energy, shaping it into a colossal particle beam that propels you outward like a surfer riding a wave of pure force. These aren't technologies, they're acts of cosmic piracy, stealing momentum from the star's own fury. But here's the ultimate twist: escaping isn't the end. The star's gravity bends trajectories so severely that even a successful launch could slingshot you into a lethal orbit, looping back like a boomerang. To truly break free, you'd need precision beyond supercomputers, navigating a path where spacetime itself is a coiled spring. One wrong calculation, and you're not just falling back, you're a smear of plasma decorating the surface of the universe's most unforgiving object. Stepping away from a neutron star's gravitational vise isn't a simple exit. It's a reawakening to a universe suddenly foreign in its gentleness. The transition hits like whiplash. One moment, your body is a leaden statue, each breath a Herculean effort against gravity's chokehold. The next, you're weightless, adrift in a cosmos that feels bizarrely flimsy by comparison. Colors normalize as the star's gravitational lensing releases its grip, stars snapping back into pinpricks instead of smeared halos. Time, once stretched like taffy, resumes its familiar rhythm, leaving your senses scrambling to reconcile the dissonance. It's as if the universe itself had been holding its breath, and now the exhale is deafening. The absence of pressure plays tricks on your mind. Muscles conditioned to fight gravity's tyranny now overcompensate, sending your limbs flailing as if you've lost all control. Your inner ear, no longer battling tidal forces that once threatened to rip fluid from your skull, misfires alarms of phantom motion. Even your heartbeat feels alien, no longer laboring against a force that could crush diamond. It races unchecked, an engine revving without load. The silence is equally jarring. After the neutron star's constant hum of vibrating crust and screaming magnetic fields, the void's true quiet is almost oppressive, a sensory vacuum that amplifies every creak of your ship. Reorienting to normal space-time reveals lingering ghosts. Light no longer bends obediently around you, making distances feel oddly flat. The constellations, once distorted into funhouse mirrors, now seem sterile in their predictability. And time, measured in unyielding seconds, feels like a crude approximation of the fluid, stretchable thing you'd briefly mastered. There's a surreal loneliness to it, as if you've been let in on a cosmic secret only to have the door slammed shut behind you. Worst of all is the perspective shift. After staring into the heart of a neutron star, even the grandest celestial phenomena, the swirling storms of Jupiter, the fusion fury of our sun, feel quaint. Supernova become firecrackers, black holes merely theoretical curiosities. The universe's scale recalibrates around that one experience, leaving everything else feeling like a pale imitation. You don't just return from a neutron star, you carry its imprint, a reminder that reality's true extremes are far wilder than our everyday cosmos lets on. Staring into the abyss of a neutron star's lifespan forces a reckoning with time itself. These cosmic remnants outlast civilizations, epochs, and even the rise and fall of entire species by orders of magnitude we can barely comprehend. While human history stretches back mere thousands of years, a neutron star cools over millions, spins down over billions, and lingers in the darkness for trillions, outliving not just us, but the stars themselves. Our entire recorded existence, from the first cave paintings to the launch of interstellar probes, is less than a blink in the lifetime of these celestial titans. This disparity humbles in ways that border on the spiritual. Imagine a being observing Earth from a neutron star's surface. To them, humanity's wars, art, and revolutions would flicker by in an instant like mayflies darting across a pond. Our greatest monuments would erode to dust before this cosmic witness even registered their construction. The pyramids gone in a cosmic breath, the internet's birth. A nanosecond blip, even Earth's eventual fate swallowed by the sun's expansion in 5 billion years, would be a minor footnote in the star's eternal vigil. Yet there's a strange comfort in this disparity. The neutron star's relentless longevity mirrors the universe's indifference, but it also underscores the preciousness of our fleeting moments. Like a candle burning briefly in a vast cathedral, our transience doesn't diminish our light. It makes it more radiant. The star's billion-year silence isn't a judgment. It's a backdrop against which human creativity, curiosity, and connection shine all the brighter. The lesson isn't despair, it's perspective. In a cosmos where time can stretch like taffy near a neutron star's surface, yet evaporate like dew elsewhere, our existence becomes a dance between insignificance and wonder. We are temporary, yes, but we are also the universe's way of comprehending itself. A neutron star may outlive us by epochs, but it will never write a poem, cherish a memory, or marvel at its own reflection in the void. That privilege belongs to us, the fragile, fleeting, and infinitely curious. To grasp the star's timescale isn't to surrender to oblivion. It's to recognize that meaning isn't measured in millennia, but in the depth with which we inhabit each passing second. The star's longevity isn't a rebuke. It's an invitation to live more fiercely, to etch our brief, bright stories against the infinite. Beneath the crushing pressures of a neutron star's crust lies one of the universe's greatest unsolved puzzles, what truly exists at its core. The leading theories sound like something from particle physics fiction, a bubbling ocean of free quarks, their normal bonds obliterated into a primordial soup. These aren't the neatly packaged quarks inside protons and neutrons anymore, they're unchained, swirling in a quantum maelstrom where the rules of color confinement break down entirely. Some models suggest this quark matter could crystallize into bizarre configurations dubbed quark stars, denser than neutron stars yet not quite black holes. Others propose even stranger possibilities, strange matter, a hypothetical state where up and down quarks mingle with their exotic cousin, the strange quark forming a stable, ultra-dense substance that could infect and convert normal matter on contact. The terrifying implication: if strange matter exists in these cores, a single fragment ejected during a collision might rewrite entire planets into more of itself, like a cosmic zombie virus. Then there are the glitches, those perplexing moments when a pulsar's clockwork spin suddenly stutters. One leading explanation points to the star's superfluid interior. Imagine the crust as a rigid shell spinning steadily, while beneath it, a quantum ocean of frictionless neutrons swirls independently. When this superfluid's vortices, tiny whirlpools of spinning neutrons, suddenly reorganize, they transfer angular momentum to the crust in a violent jerk, speeding up the star's rotation in milliseconds. It's like an ice skater's sudden spin when they pull their arms in, but scaled up to cosmic proportions. Yet some glitches defy even this explanation, hinting at deeper chaos, perhaps fractures in the crust itself, or magnetic reconnection events powerful enough to momentarily alter the star's moment of inertia. Hypermassive neutron stars add another layer of mystery. Born in the fiery mergers of two neutron stars, these unstable behemoths tip the scales beyond normal neutron star limits, yet resist immediate collapse into black holes. For seconds, or even minutes, they linger in a precarious state, balanced between gravity's crush and the furious spin left over from the collision. Their internal pressures might briefly stabilize quark matter or other exotic phases before the inevitable implosion. Gravitational wave observatories like LIGO have caught whispers of these ephemeral objects, their death spirals ringing space-time like a struck bell. But what determines their fleeting lifespan? Does rotation alone postpone their doom, or does some unknown force inside them wage a last stand against singularity? Even the star's magnetic fields conceal riddles. Magnetars neutron stars with fields 1,000 times stronger than typical shouldn't exist according to conventional models. Their energy output defies explanation, with flares so powerful they can ionize Earth's atmosphere from halfway across the galaxy. Some theorists speculate these monsters might harbor superconducting coils of protons near their cores, twisted into knots by the star's birth throes. Others suggest quantum anomalies in the vacuum itself, where ultra-strong fields spawn particle-antiparticle pairs from empty space, fueling the magnetar's fury. The most haunting question remains: where's the boundary between neutron star and black hole? At what exact mass does quark degeneracy pressure fail and gravity win? Current estimates hover around 2.2 solar masses, but a few outliers, like the enigmatic object in the GW 190421 gravitational wave event, hint that the true limit might be higher, or that some stars transition into hybrid states we've yet to imagine. Every unanswered question isn't just a gap in our knowledge, it's a doorway to new physics waiting in the dark heart of a stellar corpse. Here's something to chew on. What if someone offered you a one-way ticket to the surface of a neutron star? No return trip, no safety guarantees, just the chance to witness the universe's most extreme physics firsthand. Would you take it? Picture the scene. You're suited up in a theoretical supermaterial exoskeleton, your ship hovering over that deadly, glassy surface where time crawls and gravity could turn your bones to dust. The science you'd uncover could rewrite textbook starquakes in real time, quantum superconductivity in action, maybe even clues about dark matter hidden in the crust. But here's the catch: you'd never come home. Every second spent there stretches into years back on Earth, meaning everyone you know would age decades in what feels like minutes to you. Your messages to mission control would arrive as historic relics, your family's replies lost to the void of time dilation. Now flip the question: what if it wasn't you going, but someone else? Would you send a team of volunteers, knowing their sacrifice could unlock secrets about black holes, gravitational waves, or the origins of heavy elements? Imagine the ethical tightrope. granting consent for a mission where survival means transmitting data until the star's radiation fries the last sensor. Would it be worth it? Some might argue yes. After all, we've sent probes into the sun's corona and landed robots on Mars. But neutron stars aren't just dangerous, they're physics-breaking paradoxes where human intuition fails. Let's get existential. If you did go, what would you prioritize studying? The crust's nuclear poster structures vibrating like cosmic guitar strings, the magnetic field's writhing loops visible as auroras hotter than supernovas. Or would you aim lower, literally drilling or attempting to into that impossible core where matter stops behaving like matter at all? The data you'd gather could revolutionize energy, materials science, even quantum computing. But here's the kicker, you'd never live to see the impact. Your legacy would be a data stream, your name a footnote in papers written by scientists born centuries after you left. So hit pause and really sit with it. Would you trade your life for a front row seat to the cosmos' most violent ballet? Or is some knowledge better left to robots and equations? There's no right answer, just a thought experiment that forces us to weigh curiosity against mortality, progress against ethics, and the human drive to explore against the crushing reality of the universe's indifference. Either way, the question lingers like the neutron star's afterglow. What price would you pay to touch the edge of the impossible? From mind-bending time dilation to crusts harder than diamond, our journey across a neutron star has revealed a reality stranger than fiction, one where gravity rewrites physics and matter exists in states no lab could replicate. Think about the sheer audacity of this place, a stellar corpse so dense it packs the mass of a sun into a city-sized sphere, spinning faster than a blender blade while its magnetic field shreds atoms from light years away. Every quake on its surface unleashes more energy than all human wars combined, and every second spent there stretches into years for distant observers. Yet amidst this chaos, neutron stars serve as cosmic alchemists. Their collisions forge gold, platinum, and other heavy elements that eventually seed new planets and perhaps life itself. These extreme objects aren't just celestial curiosities, they're the universe's ultimate laboratories. They test relativity's limits with every pulsar pulse, hint at quark matter hiding in their cores, and even help map spacetime with their gravitational waves. Without neutron stars, we'd lack tools to explore black holes, understand supernova, or trace the origins of the very atoms in our phones and wedding rings. They're both destroyers and creators, remnants of dead stars that light the way to new science. But the adventure doesn't end here. The cosmos is brimming with mysteries waiting to unravel. Black holes that twist reality into knots, rogue planets drifting between stars, and quasars brighter than entire galaxies. So stay curious, hit that subscribe button to join us for the next expedition into the unknown, where we'll dive deeper into the cosmic extremes that shape our universe. Because out there, beyond the glow of our familiar night sky, lies a frontier wilder than anything we've imagined, and it's begging to be